All right. Number one, what is the unit for magnetic field? So let's start with this. I forgot to tell you the symbol for magnetic field. So we should probably start there. The symbol for magnetic field is capital B. So I'm frequently going to call them B fields. So if you hear me say B fields, I mean magnetic field. So magnetic field, the symbol is B, because of course it is. Yeah. Yeah. Now, the unit for magnetic fields is the Tesla.
Oh, like the Elon Musk thing.
Yes. It's named after Elon Musk's cars. That's totally. Yeah. And that's capital T.
Why isn't it like lowercase b? They're just be making up. What is the Z? Tesla Z? Is there a unit for Z?
There's some math applications with Z.
Okay.
Yeah.
Because I just think all these Z letters are so weird.
Yeah.
They're running out of letters. They might as well.
Oh, well, because sometimes we use Greek letters and, yeah. All right. So what equation to find the strength of a magnetic field around the wire? So here's the equation. B equals mu naught, which we'll get to in a second. There's Chase's loving all the weird letters. 2 pi mu naught.
How do you call that?
It's a weird, funky U with a 0 underneath it as a subscript. Mu naught, not nut. Mu naught. Not as in 0.
And then what's the one on the bottom?
2 pi.
2 pi, that's what I thought.
And then it's times I over R. So B is magnetic field. So B is magnetic field. I is current, like you would expect. This is a lowercase r, so it's not resistance, it's radius. But I want to make sure you understand what the radius is, because you're probably thinking to yourself, oh, it's a wire. Wires have radius. It's the radius of the wire. And that would be wrong. It's not the radius of the wire. It's the radius from the wire. It's how far out from the wire you are. Okay? So if I have a wire, so I'm going to draw a wire that's coming out of the page. Let's do it going to the right. So here's a wire. So it's got a current going to the right. It's finding the field some distance away, and we would call that distance r, the radius. And then the field itself is moving in a circular path around. Okay, so the current is going in one direction. The radius is a distance away where we're looking for the field, and the field goes in a circle around the wire. Now, it's hard to draw because I drew it kind of to the right, and I'm not good at 3D. But if it was coming out at you, so if it was coming at you in the face, the field would be going around you like this. And then you would have some radius out where you're looking for the field. Okay. You'll notice one of the things is conspicuously missing, and that would be, what the heck is this mu naught business? Well, I'll tell you. So mu naught is called the permittivity of free space. Sorry, the permeability, not the permittivity. The permittivity of free space is something else. This is the permeability of free space, which is like my favorite constant. No. You don't like that one? It's the permeability of free space. It is a constant, so it's the same value every time. And I'll give you this value. You will not have to memorize it. As soon as I show you, you'll know why. The value for the permeability of free space is 4 pi times 10 to the negative 7th. Yep, that's the value. 4 pi times 10 to the negative 7th. It is a big number. It's actually not a big number. It's actually really small. But yes, you're probably saying to yourself, Mr. B, why is pi in this? Well, it has to do with the directionality of things. Also, notice that when you plug it into this equation, the 4 pi is always going to simplify down to 2. Because it's 4 pi times 10 to the negative 7th over 2 pi. So the 4 pi and the 2 pi will simplify every time. Every time. So let's look at a quick example of this. So what's the magnitude and direction of the magnetic field 0.02 meters away from a 2 amp wire that is going into the page? And we're going to introduce something called the right-hand rule. I talked about the right-hand rule yesterday, but we're going to introduce the right-hand rule to you here. So first things first, write down knowns and unknowns. So the magnetic field is what I'm solving for. I'm given a radius of 0.02, and I'm giving a current of 2 amps. Okay, so what is the magnitude and the direction of the magnetic field? So here's how I'd figure it out. I'm going to draw a simple diagram. So here is my wire. The current is going into the page. The way you show into is by drawing an X. It's like an arrow going away from you. But an X shows going into, a dot shows coming out of, like the arrow is going to shoot you in the face. Okay? All right. So there's going to be a current, a field that's going to go around it, but we need to figure out the direction. We'll get there in a second, so let's figure out the value first. So the equation is B equals mu naught, which is 4 pi times 10 to the negative 7th over 2 pi. So the 4 pi and the 2 pi simplified down to just 2. And then it's times the current, which is 2, over the radius, which is 0.02. And then you just got to solve it.
That's not too bad.
No, it's not too bad. So 2, yes?
If it always simplifies down, why not just make 2 times negative 7?
I was wondering who was going to ask that question. So if it always simplifies down, why do we not just make the value, like why not just make the equation mu naught times I over R? The reason is mu naught came first, so we discovered what the permeability of free space was first, and then we found the relationship for the magnetic field. And we do use this value without this equation sometimes. So that's why it's like that. But in this equation, it'll always simplify down. So 2 times 10 to the negative 7th times 2 divided by 0.02 gives me a magnetic field of 2 times 10 to the negative 5th Teslas. But I need a direction. And this is where the right-hand rule comes in. So here's how the right-hand rule works. You're going to use your right hand. Okay? Nope, can't do the left-hand rule. Actually, I should rephrase it. You can do the left-hand rule, but your answer is always wrong. So all you have to do is flip it around. So if you do the left-hand rule, your answer is always backwards. So I could see why you would want to do that to be different, Sam, but it's going to just make sure you know that.
I'm left-handed, so I understand.
Yeah, just make sure that you're always flipping it around.
I was just being the spokesperson.
I know you were. All right, here's how the right-hand rule works. Ready? You take your thumb, and you stick your thumb in the direction of the current. So the current is coming into the page. So I stick my thumb into the page. Bam. Then I take my fingers, and I wrap my fingers around my thumb so that it's something kind of like this. Okay? So I'm wrapping my fingers around my thumb. The direction of the field is the direction of my fingers. My fingers are clockwise. They're going clockwise around the wire. So the direction is clockwise.
Oh my gosh, that's crazy.
So when you label it, you're just going to put like Tesla's clockwise?
Or counterclockwise. Yeah, that'll be the direction. The direction will be clockwise or counterclockwise. Now, I might ask you, like something I could ask you, I don't think I'm going to try to do this year. But you can figure out, like, if I said specifically, like I think one of these questions on the back says specifically, like, above the wire. So if you were looking above the wire and it's going clockwise around, what direction is it above? To the right. So like the direction above would be to the right. But if you say clockwise or counterclockwise, I'm fine with that for now. Okay? There you go. That's all you have to do for the math. That's it. Simple and easy peasy. Yep. Yeah, that's how many Elon Musks there are.
Oh my god.
There are so many
Sometimes I
Elon Musks
wonder
in
if
the
you
world.
speak English.